String.
String is not Spring, even though it's just the...
It is not String.
Yes. I do this talk in English mostly to the homage to those who don't speak Russians. How many there not speaking Russian? I think Marcus is here. Okay. Oh, you don't speak Russian. You do, yeah. All right. So pardon if my English is way too bad, but you can download the slides and read them. All right. This is a famous slide. I can spend 5 minutes talking about it, but I wouldn't. Instead, I will explain why I call this talk Catechism. And Catechism, if you look at the definitions in Wikipedia, it is the summary of the faith. It is just the set of questions and answers that you have, that you indulge your converts so they learn the grounds of the belief. And it's usually a very small part of the foundation of the belief, but we are trying to be rational persons, so when we talk about religions, we need to talk about this guy, who says that we are engineers and we intimately involved with science, and science replaces private prejudice with public verifiable evidence. So everything that I will tell you today is public and verifiable. You can go ahead and test it before trusting me blindly as if I'm some kind of prophet trying to tell how strings actually work. All right, so disclaimers. All tests that we will show are done by trained professionals. You can try that at home, but you have to recheck the results before using them. We are running on the very fast machine and very high clock rate machine, so the absolute numbers are not that interesting because your machines are probably slower. So look for the relative performance differences there, and we run on the latest and greatest Linux kernel, latest and greatest GTK, and driven by the latest and greatest benchmark harness, which everybody knows is JMH. All right. Why do we care about strings? Because strings are abundant. Humans communicate with text. And so machines follow suit and communicates with text as well. All our source code is text-based. Most data interchange formats are also in text. And that is why if you profile the large set of enterprise-like applications, there is the anecdotal data from one of our Java enhancement proposals. And it says that 25% of heap is occupied by string objects. And we do a lot of heavy lifting on the string objects because that's what human-facing applications do. So with the headlines like that, if we do string optimizations, these optimizations almost immediately give you the immediate payoff. And also, if you are avoiding the cardinal sins in dealing with strings, you are making your application perform better. So in this talk, we will see how strings are done on the lower level and what does it mean for you. First, for internals, how many of you actually looked into the Java.lang.String source? Nice. So you will see something like that. You'll see a lot of methods there, but you will also see two fields there, character value and hash. And the character array is final and the string is final, which means that the string is effectively final. And that means that you can pass and use it without synchronization and nothing breaks. And this is a very strong requirement for the library class. And also, because we have isolated user from the char array, we can do all this magic with the character array without user noticing because nobody actually sees that char value at all. This comes at a cost, right? What is the cost of this? If we look at the layout of the string, and this is the layout which is done on the 8.840 string, and we can see that we have quite a lot of the overhead. The string object has header, which has all the object metadata. The character array, we have the reference to character array there, but the character array itself also has the object header and also a length, which also wastes space. So if we carefully count what are the overheads, we will see that depending on the VM mode, you have 12 to 24 bytes space overhead against just a plain char array, or if you are comparing it against C, you have like 44 bytes of overhead against the vchrt, which is the white character there. So with headlines like that, people ask themselves, should I use strings to begin with? Right? If it's so overheady, should I do that? Well, absolutely, if you are dealing with the text data, because the class library is intimately tied to this string. What if that memory footprint is a concern? What if I care about the overheads? There are remedies for that. Read on. Well, you can wind up your own string implementation over char array or char sequence or something like that. Should you do that? Well, in some cases you should, but you will suffer from some caveats that we will also cover. Well, should you do that? It really depends. I have yet to see the legitimate case where you should. Some really hardcore guys just do character arrays if they really care about the string memory overhead. Strings are immutable, right? Are strings immutable? Who are for strings immutable? Almost immutable. Okay. So, and string is also interesting because in JLS we have the section which says string concatenation operator. This is one of the few places in spec when we actually reference the class from the class library. And also we have the concatenation operator there, and in spec you see that spec requires that the result of string concatenation is the string object which is newly created. That is what is required by spec. There is a caveat that if you can construct it from compile time constant expression, it may be a constant, but we don't care about this at this point. So if we do this benchmark, if we have the string foo and we try to add 1,000 bars to it, is there a problem? What is the problem? Spec requires that we have the newly created string here, because this is the result of concatenation operation. What do we do to avoid it?
Optimization.
String builder, yes. Now it works fine. So how bad it could be, actually? Well, if you measure this, this benchmark on my laptop, this is what you have. This is the throughput, the larger the better. So we have like 30x performance penalty for adding 1,000th of string. If you look closer at the profile, you will see a lot of concatenations, lots of memory activity, lots of GC, and that will probably kill your performance in many cases. This is why Findbox, for instance, tries to warn you about this and say, well, string concatenation in loop is really bad. You should really reconsider writing that. All right? So why is this painful? Because immutability almost always comes at a cost. Immutable objects always have the immense construction costs. And this is generic, this is not nothing specific about strings here. If you want to ease off the construction cost of immutable objects, you use something like mutable builders, and string builder is the one of the cases of this mutable builder stuff. Why can JDK optimize it for us? Well, it can in many cases, but there is no escape if you want the highest performance. You have to do string builder anyway. Do you need the best possible performance in all the cases? Well, it really depends. I'm not sure that you have to write the code with the builders to begin with. You should just rewrite it in some selected cases. Right? Coming up next, concat. Spec says there is a string concatenation operation, but in bytecode there is no bytecode syntax for that. There is no operation which can concatenate strings. So what should Java compiler do to fit the JLS spec? Well, actually, if you have the concatenation of two strings there, Java-C has to compile it into the chain of string builder append calls. So it actually has to instantiate string builder, do a few appends, then do toString, and get the result of this concatenation. There is no other way around it. There is no specific, bytecode instruction for concatenation there. So if you look at that, it's not surprising that string builder append chains are heavily optimized in compiler, because otherwise everything will just suck big time. So if we measure the benchmark like this, either with explicit append chains or the implicit append chains, the implicit chain here compiles by JavaC compiles it to this exact, well, almost exact bytecode sequence there. And we can try to switch on and switch off the string concat optimization in VM to quantify how bad it would be if JIT is not optimizing it for us. And these are the numbers. So in decently long append chains, you have like 2.x performance differences between these optimizations turned on and turned off. So JIT actually is able to optimize it very, very nicely. When people realize that there is the optimizations like this in JIT, they got all nervous about benchmarking. But those who are oblivious of this fact are really puzzled on the behavior of this benchmark. This is the Stack Overflow is full of questions like that. What is faster? If I have an integer and I want a string, what should I do? Should I concatenate it with empty string? Should I probably concatenate it after the empty string, which is the modern version of pre-increment, post-increment debate? Or you should just call the explicit methods like integer to string or string value of. So who says the integer to string is the fastest method here? It should be, right? It's just explicit method. Who is for string value of? It should be. It's just a class library method. Who is for concat? If you run it, now it's time, so the lower is the better. Concat actually wins a lot. And this is because string builder JIT optimizations kick in, and the append int calls are actually much faster than calling the explicit integer to string and string value of. Well, admittedly, this is the performance glitch in the VM, which doesn't optimize integer to string and string value of in this matter. But this is the real stuff, the real JDK which is out there right now. If you turn off the optimized string concat optimizations, the concat cost will be much greater than integer to string and string value of. So, as usual, the answer to the question, what is faster, concat or explicit calls, is? It depends. Nice. So now we will complicate this test a little. We will keep around the concat and integer to string. We will append just to them and just says we just concatenate them with strings. But I also want to do some side effects in that expression. So I do x++, and in order to keep the value of x in the same range, I do x minus minus before that. So do you think the, well, we know that the concat just is faster than integer to string just. Do you think that concat side is faster than integer to string side? Who's for that? Should be, right? Nothing really changes. Well, side effect, so what? Who's for the opposite? So the integer to string is faster. Well, JITs, how they work, right? If you run it, you will see that the concat side is actually slower than its counterparts there. And this is because if we have a side effect in the append call, the JIT optimization bails out, because if I do this optimized append chain and I realize that I have to throw the exception, like out of memory exception or something from that chain, I should bail out optimized code. I should rebind to the interpreted code and start executing the append chain again. If I have x++ there, it's too late to rewind the memory store or any side effect that I had there. So the very trivial optimization of actually moving the side effects out of the append calls really help JIT to produce the better code, because now I'm setting myself up for this kind of optimization there. This trips people out. I've seen 2 Stack Overflow threads when people are tripping over this. hardly. So take care of that. Lazy logging. Who does this actually? If you have a log method which accepts message, and you have the Boolean field which says enabled, even this enabled is false, people do not do this because they don't want to pay for the concatenation cost here, right? So they do explicit checks before each log statement, which sucks, in my opinion, because, well, it contaminates your code needlessly. Log should be taking care of that. Right? So what can we do here? We have lambdas, and lambdas are our power tool which can give us a deferred execution. We can rewrite log in such a way it accepts supplier string, and we can just say, well, this is lambda which will produce the string which you will print if you need to. Well, people who were at our talks, and they will say, well, so what? If you capture something from locals or from heap, you still instantiate the lambda instance, whatever that is. So you still pay something for this kind of scenarios, right? And so here we have three options of capturing something from heap, capturing nothing, and capturing something from local variable. And this is the performance data. String means you just call it with the string concatenation. String guarded means that we do this enable check before calling log, and lambda is this deferred execution stuff. Right? So you can see that the improvement between string and lambda is immense. There is a difference between lambda and string guarded, so if you need a peak performance, you have to probably still do this kind of tricks of explicit enable checks there. But if you don't care much about this difference, you might as well just use lambdas. That's it. So, should I be worried about concatenation costs? Well, you should in all non-trivial cases. What cases are non-trivial? These are any patterns that involve control flow, like you have a concatenation in the loop. This is a control flow. You have side effects in your concatenation operators, or you have unpredictable values, like you have volatile reads in the middle of append chains or something like that. Are string builder flawless? So if I write the string builder append everywhere, will I get the maximum performance there? Well, the case for side effects tells us that we have to do some extra work in some corner cases to have the maximum performance there. Well, if you are coming from other languages and say, well, this is nuts. Just give me a call by name or lazy val and we'll pick up from there. You can still do that for lambda and avoid this concatenation costs by deferring the execution of this thing. Hash codes. String hash code. Who knows how it's defined? All right, this is how it's defined. This is the on the left is the academic definition of it. It's the polynomial P31 hash code. And on the right is the actual implementation, which is really, really simple. You just go and compute this polynomial by multiplying by its root there. And you can see that the cost for this hash function obviously depends on the string length, right? So if I go ahead and do this test, I have two strings, same length, and I request hash code over and over from these strings. Do you think the performance of this method would be equal? Who is for equal? Same length, should be the same performance. Who is for different performance? Yeah, runtimes, how they work. So if you run it, it will be like that. Any idea why? Actually, yeah. The actual hash code looks like this. We have the field hash in string where we cache hash codes, and it helps lots of real applications. And we have to have a special value for this hash code which says, well, hash code has not computed yet. Well, some strings would have the hash code 0. Well, sucks to be them, but that's what we have. And it is a sane engineering trade-off to say, well, we can have the performance anomaly with a very low probability, but will not waste any other space anywhere. And we will just use this point value to figure out the special value. The next example, walking on sunshine. We have the map, which is called sunshine, and I carefully populate it with my data there. And I want to walk it through key set or the entry set. And black hole is the JMH way to avoid that code elimination for these things. So, generically speaking, what benchmark is faster? Who's for key set? Hash maps, well, just a hash map lookup. What's wrong there? Who's for entry set? Generically speaking, entry set should be faster because it just walks the storage of hash map, and the key set does the lookup for every key. So if we run it on my carefully constructed contains there, this is what we'll see. This is the time for test, and this is the size of the map, and this column is normalized. This column normalized by this column, right? And for intercept, we say, well, okay, it's like 10 nanoseconds per key. It's not that bad. But if we go through the key set, we will see that the performance is rapidly deteriorates. There's like quadratic performance there, which is obviously bad. So what's up? Why? I actually generated lots of strings with the same hash code. And the sad part is that this hash code makes it really easy to generate collisions. So we have had this computation of hash code, and I peel the two last characters from this hash code. And I have the strings which have the common prefix, and so this part here is equal for both strings. I have to solve a very trivial equation here to find the strings A and B which has the same hash code. Surprisingly, it's very easy to do. If you have the common prefix and you add up AA and BB, that is enough, because the difference between A capitalized and B capitalized is 1, and the difference between A lowercase and B capitalized is 31. So it's enough to have the collision on that. Why do I have to care? Any ideas?
Security.
So I have this battle-hardened HTTP server. I patch it up. I follow our CVEs, all this stuff. But then some guy comes along and say, well, here's your HTTP request with carefully constructed HTTP headers, and my servlet container or something like that puts the HTTP headers into some sort of hash map, because it's the obvious thing to do when you process the HTTP headers there. But if I construct it carefully so that these keys have the same hash code, which polynomial hash code makes it very easy for me to do, then this is the scenario for denial of service. Because I can very easily put your application server to its knees when it tries to process this request. So how do we avoid this?
Use Java 8.
What do we do in Java 8 to avoid this?
You put all the buckets into the tree.
Yes, so now in HashMap we secure ourselves by handling the collisions in each bucket by constructing the binary tree, not the linear list. And so we have and log n performance. Well, actually, a lookup is now log n in the worst case, and we have to do that for each key. And you can see that the degradation is there, but it's not that much. So it's not a denial of service scenario. It's just gracefully degrading or something like that. When you look at the research for the hash codes, you also see lots of interesting stuff, like CRC, for instance, which does somewhat the same thing, well, a little bit the same thing, says that if I have like the preceding null bytes in CRC computation, then no matter how null bytes I have in the beginning, they don't count to the CRC hash code if I initialize it with zero. The same applies to hash code. If I have a string and I prepend the arbitrary number of null characters before it, it will still produce the same hash code, which is also the scenario I have to care. Frankly speaking, I've thought this is a very specific case, but we've seen the bug reports when people actually do this kind of stuff. And they wonder why their hash maps are not scaling that well. Well, because we are initialized at 0 and our first bytes do not count. So should I care about string hash code? Most likely not, unless you expose your naked maps for human input. Should I wrap the strings with my own hash code implementation? In some very rare cases, yes. I think Yelizarov is here, right?
No, he even talk.
Oh, okay. Well, if he was here, he will tell the case when there is a reason to do that. Why don't we change the string hash code computation? Seems easy to do. We can't really. The hash code computation is spec'd in so many places, in JVM spec, in JLS, in Java.lang.String, Java-doc, and all this stuff, in all the different places in VM, in Java-C compiler, and all this stuff. We can't just change that. We can't even, say that the 0 is the special value. If you have the hash code with hash code 0, we just magically pretend it's 1. We can't. It counts as the change for the hash code implementation there. Some people say, well, the probability of hash code 0 is not that low, so can we do a Boolean flag there? Most likely not, because it will explode the string footprint even worse in some corner cases. Substring. When you look at the implementation of string in Java 8, you will wonder about two things, I think. Any surprises when you look at this thing? These are two fields in string. Anything missing?
There was two fields additional left.
Yes, where are offset and count fields, right?
Java 7.
Huh?
New Java, yes. The one.
Oh, okay. Well, yeah, sorry about that. But here they are. Here are the fields. They are left in JDK 7 update 6. I will explain the reason for that a little bit later. Now, if we go ahead and try to benchmark the substring implementation, this is a good thing when you start to use APIs to get the feel of what's performance modeled there. If we have the long string and we start to do substring up to the limit, and limit is the configurable parameter for the benchmark, do the substring from the start and from the end. If we do that in JDK 7, this is what you will have. You don't really copy anything. You just say, this is the new string, the offset and count fields are recomputed, but it still shares the same character array, which is good, right, for us. Well, it turns out that in many enterprise applications, people do some wild stuff like loading up in XML, which is 100 megabyte XML, then do a substring for the single XML entity, and then say, well, we just copied a few bytes there, so this is what is retained from that string there. And then they realize that they have spurious out-of-memory exceptions because they actually share the entire blob of this character array. So in JDK 8, substring is now copying. So if that avoids memory leaks, and it works reasonably well for small substrings. And the question that you obviously have, well, new substring sounds bad, can I get it back? No, you can't, sorry. Why? Because real memory leaks are much worse than the potential performance issues. Performance issues substring you can at least see in Profiler to see what's wrong there. What if I need the constant time substring? Well, that means you care enough to actually produce your own storage.
Why it's not configurable via flag?
Because it is a very intrusive change in JDK and VM. You wouldn't like to do that. You will introduce like 1,000 bugs there, and it will be all worse. Trust me on that. Intern. Any interns here? All right. It irritates me when people confuse intern with deduplication. And let's clearly separate these things. So if you have the set of objects and you have the equivalence relationship defined on this set, like equals, for instance, that means that this set can be split in the equivalence classes. Deduplication is the process when you try to reduce the number of instances in each equivalence class there. Interning is the extreme case of deduplication when we reduce the number of instances in each that class to one canonical instance. Do I make myself clear? Well, it's the basic set theory, come on. If you look at these two properties and you have the performance experience, you will know that enforcing stronger property almost always costs more. So which is the stronger property? Which is the stronger process? Deduplication or interning? Who's for deduplication? I feel like an idiot here. Who is for interning? Nice. In many cases, people do not want interning. In many cases, people want just the deduplication. But even if they want interning, it's rather easy to do the interning by yourself. You just do this concurrent hash map, put if absent, blah, blah, on call, some of those magic methods then that, yeah, those guys have in their bloody enterprise. But it's easy. It's just the workable interning code. If I do this kind of interning, and I also have the version for the hash map, which would not be thread safe, this is a thread safe one, and compare it against string intern, this is what I'll get. And this is the times of the bigger is worse. And you can see there that the string intern is order of magnitude worse than hash map or concurrent hash map. Why is that? It's the library method. The common perception is that if that's a library method, that those folks at Oracle had actually optimized it to extreme, which is always make me, well, giggling. Why?
You are using the wrong startup parameter.
Startup what?
Startup argument. You are using the wrong one.
Oh, yes. So it turns out that when you do the string intern, you are actually adding the strings to internal VM string table. And that string table at this point in 2014 is fixed size for some weird reason. Well, it's legacy code, legacy C++ code, which, right. And it's really overloaded. I put 1 million strings there, and I have a hash map which has the average bucket size of 16, which is not the mode in which hash tables operate nicely at all. And if you try to stuff your strings there in this strings table, you only make it worse for everyone, including yourselves. So the throwaway interner that you can wind up there and you can actually give it up and remove all the storage as the garbage is actually a better idea for interning. If you relax the requirement for interning and instead try to do deduplication, some other options are up to you. So now I can do, for instance, the probabilistic deduplicators there, when I can have the probability with which I would deduplicate this instance. If I have this probability, this is a knob which can help me to finally tune the memory savings against the deduplication costs, which can matter in the high performance environment. So if I run it, well, I can see that as I grow the probability, the costs actually grow up. And so I can look at that tables and have the educated guess what is good for my production environment and do that. And also if I have this probabilistic deduplicators at some fixed point where there is the entry into my API, I can actually try to gradually deduplicate all the strings that I'm operating with. If I have a reason to care about footprint, it's not the general optimization anyway. Why can JVM do that for us? Well, apparently it does. In J1 we have string deduplication feature, which is there in 8 update 20. Who is familiar with that? Yeah. So let's try to do this test. We have the list of strings there, and we use the tool from OpenJDK to estimate its footprint. We just, wait for GC to deduplicate this stuff, and we print the footprint information. This is how it looks like. The original, we have an instance of array list, which has the array of objects. They have 10K strings, which has the backing character arrays. After deduplication, GC actually can compress, deduplicate this character arrays there automatically without you, noticing, because we had encapsulated char anyway. You don't get to see it. Why can't GC deduplicate strings themselves? Can I deduplicate the strings themselves? Who is for it can? Come on, it should be smart, right? Who is for it can't? Why? You're just repeating what that guy said. Yeah, well, it can't, because if you have the two different references these references to different strings, it should stay the same by Java rules. You can't just magically make them appear the same. So if I cut it through my own deduplicator, I can also reduce the number of strings, and it will also give me the footprint improvements. But I read so much about using string intern for memory footprint. I think this is the instance of Hanlon's razor. Those guys just have no idea what they're talking about. They have never actually estimated what are the costs of using string intern, for God's sake, because the very basic test shows you this is not a good idea. But I will use the string intern on this tiny little location here in my code, on this line. Well, good. You already know where your bottlenecks would be. Usually just blanket removal of string interns and replacing it with throwaway interners is the immediate performance boost in most scenarios. Well, why can those idiots at Oracle optimize string intern? Well, we are optimizing it, but it doesn't help us from the misuse of string intern. String intern is not here to deduplicate strings. It's the gateway to hellish VM's idea of scalable hash table, which is not what you want. Should I rely on GC deduplication for ultimate memory savings? Well, no. Probably you have to do it yourselves, because identity rules, blah, blah. Equals. Let's first have a simple test. We have this string bar A, and we try to compare it against different other strings. So this guy compares the string against the string which is the same character-wise, the same length, same character-wise. Two other tests have the same length of the strings, but they differ at the end or at the start. And the fourth one has the strings of different lengths. So which test is faster?
Different length.
All right, let's see. Same char is actually faster, because those are compile time constants. They are interned by JLS specs, so you have the instance comparison, and it's very fast. Strings of different lengths are not compared at all. So probably instead, if you carefully study your strings, you will probably notice that it doesn't worth to intern strings to have this equals checked there, because most of the time your strings will fail the different length check. And also you can see that we compare from left to right, which means that if you have the difference at the end, it costs more. So then people look at the equals implementation, and they see, well, I see this guy here, it looks like C, it's probably a C port, so it's probably fast. And you can really not optimize anything there. You have this very high performance C programming idioms like increment, decrement to 0, and all this stuff around, pre-cache it in locals and all this stuff around. And so what trips people over is that equals is actually intrinsified. It is an intrinsic in our compiler. We will produce the more optimal code for this kind of stuff. So if we disable the intrinsic, we have the special option for that. We have like 2x performance difference when we start to actually compare the strings there. So how on earth we can have the 2x faster performance compared to this very optimal version? Any ideas? We can actually do comparisons in strides, depending on what is available on our platform. Like here, you compare these guys by in 4 byte strides there. If we have SSE, AVX, or something like that, we can efficiently compare with those instructions there. It sure beats the comparing by character. And we don't care if VM auto-vectorize or not. So I have this very nifty idea of optimizing string equals. You know, people look at Java code and say, well, you can just rearrange some stuff in Java code and it will get better. No. If you don't prepared to deal with all the VM-specific stuff, which is optimizing it for particular platforms. Don't even start. Why do we have this Java equals implementation in Java? Because, well, interpreter, non-optimizing compiler, and all this stuff around is still using it as the fast fallback code. Well, should I intern string and then use equality? Well, you can just compare on hash code, which is cached, or rely on the fact that the equals check will probably fail on length, which will give you all the benefits already without the mess of interning. Regex. Now I have two problems, right? I have a sentence, nonsensical sentence in Russian, and I want to split it in words. So what I do, I have a split method in string, but this split guy accepts regex, actually. So I wonder, what is the performance difference if I split it by 1 character or by 2 characters? In order for this guy to produce the same result, I have to multiply the number of spaces here. Or I can just use the pattern compile and do the split there. Which method is faster? Which? First one. Why? Let's measure it. There is a fast path for splits which does the single character splits, because it's really easy to do. If you have something more complicated, then you have the full-blown regular expression match. If you cache the pattern, you save a few cycles, but you still have a full regex match there. And it also trips people up when I parse the output and I say, well, I have the space-separated records in my file, and so one time I realized that I have to match also these 2 consecutive strings, 2 consecutive spaces, and I add a single character in my split pattern, and my performance blows up because I'm out of this fast path there. And people who also look at this method say, well, I don't care, I would not use regex at all. Well, lots of string methods actually uses that implicitly anyway. So if you care about performance of this method, it's probably a good idea to just inline it and pre-cache the compiled pattern. It will save you a few cycles. Okay. Now the horror parts of regular expressions. So suppose we have this regular expressions which says x plus capture group x plus y. And we want to match it for this text, which has a y on the end. This text obviously matches this regex, right? It does match it, right? So if we have a different text size and we increase that text size, well, we have more work to do with larger text, so the performance degrades a little bit. But then we try to match this guy who doesn't have y on the end. This text does not match this regex. And if we do that, we will have something like that. And this is a very widely known issue with regex. In some cases, it can catastrophically backtrack. It has to figure out how to split all the access in the text between these capture groups here. And because this text does not match regex, the regex engine have to try every single possible distribution of this access for this regex, which just exponentially explodes. And this is the exponential growth there. So we have a web application which accepts the regex from users to search through the mountains of data you have. Or you have the user input, which is then being parsed by regex. This is the denial of service scenario for you. Careful guys will construct, or some morons will construct the input which will do the denial of service on your environment. Should I really care? I would never use regular expression. Well, yes, you will. And you have to learn now how to deal with their problems before it's too late. It's not fun to come to work and see that your application server spent 18 hours trying to do regex matches because it catastrophically backtracks and you haven't heard about such a thing before. I've been there. Not a good idea. What are the major improvements that I can do? Well, I can simplify and cache patterns. Catastrophic backtracking sounds very theoretical. Do I have to care? Yes, you do. It's not that theoretical. Happens all the freaking time. Regexes are done. Walking. We are coming to the end. This is a very frequent question on Stack Overflow. If you have a string, what is faster? To walk with the char add or dump the char array and walk the char array? So which one is faster? First one or the second one? Who is for char add? Who is for char array? If you measure these guys on the different text lengths, we will see something like that. Char add actually faster, even though it has the explicit bounce checks within it. JIT is still able to optimize out these bounce checks from there. And 2char array pays for memory allocation. It also has the bounce check eliminated from there, but now I have to do the actual copy there. Let's make it interesting and add the method which I called spoiler, which is non-inlineable method, which we don't know what it does, it's just an empty method there. What is faster, 2char array or char add at this point? Who's for char add? Oh, come on, have some belief, you know. Who's for 2char array? If you measure that, we will see that the char add is actually slower because now VM is unable to track text. In this optimization, I have no idea what this text is after the spoiler call. It might as well change the text or do something nasty about it, right? So all the optimizations that eliminate the bounce check with char add and all this unrolling stuff is not working. And here I escaped that by cheating. I actually copied the contents into my local variable, and so it's not susceptible to the same kind of breakage there. So should I copy?
Can you show the first version?
Yes, here.
Could it be that in your second variant you taking the length from the text and it is somehow...
Oh yes, I changed that in my test. Doesn't matter. Okay. So should I copy char array or not? Well, if you don't need performance, both are, the choice is actually the question of style. If you care about performance, should I copy the char array? Well, you have to if there is a non-trivial case. What is non-trivial case? It's the non-local control flow, volatile reads, and all this nasty things that can break the optimizations in that loop. Well, why there is no universal best performant way? Well, because there isn't. There's no such thing as the universal best performance way. All right, and the last section here, search. Before that, oh yeah, we will do some basic examples there first. We have a string which is just the alphabet, and we figure out what are the performance costs of index of, last index of. They are obviously linear cost, and index of searches from left to right. This is why it grows in this direction. Last index of searches from back to beginning, so it grows in this direction. This is kind of the obvious stuff, right? So people, again, look at the index of Java code, say, well, we will optimize it. Not gonna work. It's still intrinsified. So we have intrinsics for index of, and we also use the vector extensions to search there. On larger text, the performance improvements are actually much greater. There is no intrinsics for last index of because, as far as I know, x86 has no operations which can search the string backwards, and it doesn't really matter and makes sense to search from the beginning there. But now for something interesting. Those are synthetic examples. Now I go to the Human Genome Project and download the Human Genome, which is the huge slob of text data. And I have a human Y chromosome. I have an intimate relation with that particular chromosome. And I tried to search some sequence of codons there, some sequence of words, of letters there, which I know are at the end. And if I try to do this with the string index of search, it takes around 50 milliseconds per hour. And then I say, I don't believe those Oracle guys, rightly so. So I go to Wikipedia and I copy the textbook example from Wikipedia to my benchmark, which does the Boyer-Moore searching in the string. And just the textbook algorithm is faster 3 times than this index of. Intrinsics are not winning me much. The Boyer-Moore is asymptotically better than the trivial search. So if you are working with the huge slabs of data when performance matters, you have to have the algorithms which are tailored for your use case. You can't really get around that. So asymptotically better algorithms are good. Why don't we have a Boyer-Moore for index of? It's an interesting question. Most of the time, index of are called on the small images, on the small search patterns there. And Boyer-Moore requires preprocessing. So it requires memory, it requires time to preprocess the image before you start the search. And somewhat anecdotal case is that if I do pattern blah blah matcher find, I will realize that this guy actually uses Boyer-Moore. Because now I compile the pattern anyway. I can do the preprocessing there. So if I have my automaton which matches my regular expression, and I have the node there which matches the entire substring, I might as well generate all the Boyer-Moore tables there and use the Boyer-Moore there. So I can have this kind of gem there. It's one of the rare cases when regex are actually faster than trivial things. Right? Why is there no optimal string search algorithm in JDK? Well, because optimal is in the eye of the beholder. Why would we maintain the trivial index of? Because small images are still working better. Well, and bioinformatics sometimes do that. They say, well, Java sucks for this particular domain, so because of this tiny little detail. And you just say, well, go ahead and do the third-part library, and your life is better infinitely from that point on. Conclusion. This actually sits there on the whiteboard in the Stockholm office for some weird reason. There's some sort of shrine there. It's actually me doing this, doing the exceptions talk, the preparation for the exception talks. What can be learned from, not that image, but the entire talk, that the strings are well optimized, and the learning when optimizations are working and what optimizations are there can help you to employ them in your applications. Learning what JDK and JVM does is a useful skill in this matter. Brian Goetz says that the performance advice has a generally low shelf life, so we can change things as we go. So for instance, I think we will optimize index of for the larger images at some point and do the Boyer-Moore there. So don't trust folklore. It doesn't really take you that much time to learn the basics of basic performance models of the methods that you are using all the freaking time. And at this point, I say that's it.
Thank you, Aleksey. We have some time for questions, and also please don't leave this hall. We'll have some kind of ending here. So, your questions?
Yes.
Why don't you reduce the memory footprint of all programs by half by introducing 1 bit? Is it the 8-bit string or not?
We actually tried that. We tried once to have the strings which are ASCII strings, which you can represent in 8 bytes. But it turns out that the library methods which operate on Unicode characters require unpacking it back. So in realistic applications, the costs of translating it back and forth is actually greater than the memory footprint savings and the associated craft that you have in your heap than actually doing this kind of stuff. So it's not an easy answer.
But we are making some experience. We still continue.
Yeah, we still do that. Oh no, don't ask it. All right, go.
Okay, in that example with backtracking, why can't Java just use proper regular expression engine and do not backtrack? There are lots of them.
As far as I know, any regular expression engines that supports capture groups require this sort of thing. It either has to do the non-deterministic finite automaton and has to backtrack there to have the full match, or they have to execute it and have the exponential execution time, or they have to construct the deterministic automaton, which is just the exponential in size, but runs in the constant, well, not constant, but linear time. So there's no easy questions here. Don't harass me about that. Go and harass the regular expression guys. I'm just a messenger. This is what happens in production.
It's very famous type of attack, language independent.
Yeah, I know. But most people don't, surprisingly. They say that I just exposed this pattern, nothing bad will happen. Well, how bad could it be anyway? It's not like shell injection or whatnot. But it's still performance. Yeah?
You mentioned several issues which could cause denial of service attacks, like attacks for hash map, conditions and so on. Comparing strings without comparing hash code beforehand could also cause the attacks. When you pass very long strings, which differs only by the last character, if you compare hash codes beforehand, you will eliminate it.
Yes. So again, this is not an easy question as well, an easy answer as well. So I have to learn more about this stuff. Probably it's not worth to do hash code. So it really depends on what strings do you have in your stuff. What do you want to ask?
Yes, I have a question.
You want the card for the unconference? I give you it right now.
No. Just need an answer. Please show slide who's working in case of non-aligned functions.
Here. Yes.
Yes. Why? Just not to save global variable text into some local variable in the first case and got every benefit from bounds check elimination even with not inline function.
I tried that and I think it still doesn't work.
So I just want to know the detail.
Yeah, it still doesn't work because you can have like some crap, some reflection crap, which can still.
I'll recheck.
Yeah, go ahead and check it. It should be verifiable. Maybe I'm wrong. Well, it happens. Any other questions? Oh,
it probably has an obvious answer, but I'm going to ask it anyway.
Yeah.
Why does the compiler optimize string concatenation operations, which are in a single statement, but it doesn't optimize them with a string order? Those ones are a loop.
There's a short answer and the long answer. And short answer is that if you do compilers, that's a very mammoth task to do. Unwind the cache control flow and optimize it, because you can have. I think you can have the effects on each iteration which can break your optimizations there. And the long question is the is the variant of the short question, but with much more swearing in it.
Fair enough. I think that's enough.
Yeah. Any other questions? All right, get this guy a card.
Well, I think we run out of time. So, other questions, please to speaker. Окей. Остальные вопросы, пожалуйста, лично. Спасибо.
Right. Thank you.